Use the paired foot length and height data below. Is there sufficient evidence to conclude that there is a linear correlation between foot lengths and heights of males? Based on these results, does it appear that police can use foot length to estimate one's height? Okay, so, oh, and the foot length and the height, they're both in centimeters, excuse me. Um, Clearly, we are doing a hypothesis test because it says test the claim. So here's what but we're testing the claim, or yeah, we're testing to see if the two sets of data are linearly correlated. Okay, so so whenever you test for correlation, for linear correlation, you're going to do rho equals 0. Okay. And that means no correlation. Okay. And rho not equal to 0, Greek letter rho. And that means yes correlation, for lack of a better expression. Okay. So if we go with HO, no, they don't appear to be correlated. If we go with H1, they do appear to be correlated. Okay. Um, all right, so we got to plug the data into the calculator. So we're going to go stat, enter, and oh my stars, look at that, it's already there. So one list there, the other list there, and you can't mix and match. So just because these are matched data, so 25.7 and 175.3, that's the same person, so they have to be side by side in the calculator, which I'm sure you would do. Then we'll say, all right, well, let's quit out of there and go to stat, over to tests, and we're going to go up to linreg t-test, linear regression t-test. So we're checking, we want to do linear regression, linear correlation, but we also want to do a hypothesis test. So that makes sense that this is the guy. So our data are in L1 and L2. Make sure, I think the default is like this or this, but we want to make sure it's not equal every time. I stuck Y1 in there. You don't have to, whatever. Okay. Calculate. Let's see what happens. And okay, so there's a couple of ways you can explore this. One is the p-value, which is 0.08, which is greater than alpha, which oh, I didn't include that, did I? Oh well. Alpha, we're going to say is 0.05 like it normally is. I think that's what it was supposed to be, and I just didn't write it down when I transcribed it into Zoom. Um, so it would appear, based on the p-value, that we're going to go with HO, no correlation. However, there is another way to explore this, and for this will be our main way. Okay. I don't know. I think I know where we were at. I just stepped away for dinner for a while, and my wife made this stuff called bubble bread with all these herbs and spices grown in the backyard. I mean, I'm telling you, it was amazing. Everybody went away full, and there were definitely no leftovers. Okay, so another way of determining if we go with HO or H1 is to look at table A6 in the back of the book. Okay. Um, and so I know it's really hard to read. It's pretty much illegible, but you can look at it in the back of your book and you'll have it on the test. Okay. So um, let's see. This one right here, or I'm sorry, this one right here says A equals 5. I know you can't read it. And it says, oh, and then right here it says, okay, so we're interested in what's going on when alpha is 0.05 versus 0.01. So they're always going to give you a level of significance of 0.05 or 0.01. I can't draw on it, otherwise I won't be able to get back the other stuff I had. Okay, so at least I'm not sure. Anyway, so A equals 5 right here. Okay, when alpha e or I'm sorry, when n equals 5 and alpha equals 0.05, we're right here. Oh, poop, I just did it. Okay, well, whatever. Um, so we got that. Um, and that number is 0.878. Okay. 0.878. All right. So what do we do with that? Well, we want to compare that with the R value, the Pearson correlation coefficient, which was right here. And the R value, let's see, we got to go down arrow a little bit. Okay, down at the bottom, 0.82 fix, 0.827. Okay. All right, so 0.827 is our R value. So, um, let's see. Um, because at the bottom of the um, of table A6, it tells you how to use the table. Okay, it says, I should have got my glasses. Doggone it, because it's kind of small. Okay, reject HO if the absolute value of R is greater than or equal to the critical value in the table. So, is the absolute value of R greater than the critical value? No. Oh, it's not. So we are not going to reject HO. Okay, we are going, oh, excuse me. We're going to fail to reject HO, and therefore we assume that there is no correlation. Let's see if I can get that stuff back. Okay, I did. All right, cool. All right, so we're going to go with that guy, which we were already going with, due to the p-value. Okay, and I have not written one of these out in a while, so I probably should. And so, hang on to your potatoes, said Short Round. Um, so at the zero point zero 0.05 significance level, there is insufficient evidence to reject um, um, the claim that um, foot length and height are correlated. Okay. So with that in mind, um, the follow-up question says, um, based on these results, does it appear that police can use foot length to estimate someone's height? Okay. Well, first of all, no, because um, we said, hey, there's no correlation. All right. So if somebody, so like if the prosecuting attorney comes in and says, ho, 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 we found these footprints and it, measures up pretty darn close with um, the height of the defendant. So yeah, looks like, I think we found our defendant. But then the defense attorney will say, I don't think so. Um, because I've got this statistical study saying, nah, there's no correlation. But then the prosecuting attorney would probably talk to a statistician and say, oh, I don't know. I mean, your sample size is 5. I mean, you've got n equals 5. That's nothing. You got to have something quite a bit more to be significant. So I'll be honest. When I started this problem, I thought, oh yeah, there will be correlation, but the sample size is so small that it had to be really close in order to go with H1. Um, so that's kind of what's going on there. Also, you probably see this problem in the book. I changed the wording just a little. Notice it says, does it appear that police can use foot length to estimate someone's height? Well, the data comes from heights of males, not heights of females. So you cannot use these results for women or for children, okay? Because it's for adult males. At least I think it was adult. At least, well, males at the very least. So yeah, so that's another reason why the answer would be no. All right. For 30 recent Academy Award ceremonies, ages of Best Supporting Actors and ages of Best Supporting Actresses are recorded, and the 30 pairs ages yield the following. Okay, so let me make sure we all understand what's going on here. This is recording, right? Yeah. Okay. Um, so we have X bar. So that's just X bar. So that would be the mean of the X's. Well, the X's are the actors, and the Y's are the actresses. The actresses. Okay, so the mean age for the best supporting actors was 52.1 years old, and for the actresses, the women, was 37.3. Okay, and we're not testing a claim. We're just finding the best predicted value of Y for 1982. Okay. So that is yeah, where we are going. Okay. Now, the fact that they don't give us more information kind of tells us which direction we're going to go with this. Okay. But let's pretend we weren't thinking about that. Okay. So what are we going to do? Are we going to use the formula to to make our prediction, or are we going to do something different? Okay. Well, we are looking to predict the age of the best supporting actress. Okay, we're looking to predict a value for Y. Um, okay. And oh, I guess they did give us the information we needed. Okay, I misread it, even though I wrote it correctly. Okay, so now this was written probably, I'm taking this out of the textbook, and I mean, this was all put together, I don't know, probably around, no, certainly no later than 2020. It might have been 2015 that this was published. Okay, give you it's certainly later than that now. I won't tell you what year it is now, but because I don't feel like it. So what do we do? Okay, so there is a table in your book that now this time it copied really nicely. Okay, um, there's a table that tells you how to make how to decide what to do. Okay, so we're going to go clear all drawings for a moment. Okay, so is the regression equation a good model? Well, I don't know. They didn't get so the regression line graph and the scatter plot shows the line fits the points well. Okay, so they don't give us the data to create a scatter plot. On a lot of the problems they do, so you can make the scatter plot and put the regression line there and see what you think. But on this one, they didn't give that to us. Okay, well, that's okay. Sometimes you don't get all the information that you want to make a decision. So, hey, that's life. All right, the second bullet. R indicates that there is a linear correlation. Okay, well, our R value is 0.076. That's not good. Well, well, I should say that is not close to one or -1. In fact, it's much, much, much closer to zero, and zero is where there's no correlation when R is zero. So, so it sure looks to me like, no correlation here. Not to mention the p-value is really big, suggesting no correlation. I mean, the p-value is way bigger than any alpha value they're going to throw at us, like 0.05 or even 0.10. So those things are making me think, yeah, I don't think that that the line of best fit, even though it is the straight line that best matches the data, I don't think it's a good match. Okay, third bullet. The prediction is not much beyond the scope of the available sample data. Okay. So we are interested in what's going on in, okay, I should probably let me change this a little. Where's that one page? There we go. So we're interested in what's going on in 1982. All right, so that's why I gave you the year. So let's say it's 2015 right now. 30 years ago, it was 1985, the year we all went back to the future. Okay, so I was, well, younger. Um, so, and so we're interested in 1982. Well, 1982, yeah, that's not far from what was going on in 1985. Now, if they had said, "Hey, let's estimate, let's use the equation here to estimate how old the best supporting actress was in the year 2030." It'd be like, oh, okay, well, our 30 years of data runs from roughly 1985 to 2015. And is this close enough to that range? Probably not. I wouldn't think so. You're probably going to want to be within 5 years. And so, but the 1982 is quite close to that range. Okay, so let's go back to the flow chart. Okay. All right. So the first bullet, no conclusion because they didn't give us data for scatter plot. Second bullet, it definitely looks like there's no correlation. Third bullet, the prediction is not much beyond the scope of the available data. That's nice, but but the second bullet still strongly suggests that there's not a good linear correlation. So we're going to go with no. It doesn't appear to be a good correlation. It's not a good model. The equation is not a good model. Um, so our prediction is just going to be y bar, the mean of the y values. That's it. Okay. So if your answer is no, you just go with y bar and that's it. I know it seems kind of like, really? That's all? It seems anticlimactic or something. So our answer is going to be what was y bar? 37.3 years old. That's our answer. Okay. Now, what if we had had something like instead of r equals 0.076, we had something like r equals 0.9. Okay. A much, much stronger R value. And I might as well change the P value, even though I'm not really looking at it too much for this section. We'll change it to like 0.001. Okay, so now the R value suggests, oh yeah, I'm thinking there's a correlation here. Okay, so we go back to, where was it? Right here, the flow chart. So first bullet, inconclusive. Second bullet, now it looks with the 0.9, looks like, yeah, okay, I'm pretty sure there is a correlation. Third bullet, yeah, that seems okay. It did before. So we'll go with yes. And in that case, we would say, all right, well, let's actually use the equation. Okay. And so if that had been the case, we would say, all right, so so the height of the best supporting actress in 1982 would be, let's see, X would be 46 years old for the man in that year because X is the man. And I am not going to do that in my head. We'll be here all day. Okay, so I'm going to go 34.4 plus 0.0547 times 46. So we estimate 36.9 years old. Does the answer seem reasonable? Absolutely. Okay, and not too far off from that 37.3 that we had before. The difference would have only been 0.4 years. Okay, and 40% of 12 months is about 5 months. So that's a difference of about 5 months. Okay. So anyway, that's how the flow chart works in this section. Okay, this time, the Dirt Dude Topsoil Company in Price, Utah sells topsoil. I did Price because, well, there's not really any good soil there. It is sold by the yard, which is actually a cubic yard. Okay, a yard is just length. So It's like, it doesn't make sense to say, to technically to say yard. And so you sell it by the cubic yard. So it's 1 yard by 1 yard by 1 yard. And then it makes a big cube. And that's usually how you buy soil, dirt, concrete, decorative rock, by the cubic yard. But everyone just says the yard. If you're in a metric country, I would imagine it's the cubic meter, which is slightly larger. Okay. Okay, and the variable x is the length in actual yards of each side of a cube of topsoil. Construct a scatter plot and identify the mathematical model that best fits the given data. And these are the types of functions we're going to use. Okay, so this problem is actually, uh, you know, would easily find a home in an algebra class. Okay, so here's what we're going to do. We'll go stat, enter, and we're going to plug in all the data. And again, there's not that much data here, but that's okay. If you're doing this for, some other like a situation outside the classroom, then you're going to try to find more data if you can. Okay, so we've got all the data in there. We have essentially our x values and our y values. Okay. Now, we want to know which one of those models, linear, quadratic, logarithmic, exponential, and power, is going to be the best fit. Well, one thing that's good to do is, well, get rid of that old equation, is turn on plot one and go and say, hey, let's take a look at what does the data even look like. So let's go zoom 9. Oh, whoops, I've still got box and whisker display on from another class. Okay, so, oh, wait, no, I want it on, but I don't want the box and whisker display. I want this guy. I want the scatter plot. Okay, that was on second y equals. Okay, so now let's try it again. Zoom 9. Okay, there it is. So if I look at that, I can immediately say, I don't think linear is the way to go, straight line, because it doesn't look linear. Okay, it looks curvy. Okay. So I'm pretty darn sure that linear is out. Okay. It could be that quadratic is in. Quadratic does one of these things. Okay, that's what quadratic looks like. It probably is not exponential because unless you really fiddle around with this thing, which I don't think the calculator does, exponential looks like this, like the inverse of what we're looking for. That's what exponential looks like. I'm sorry, logarithmic. Okay. Exponential does look a lot like that. And power model also can look like that. So my money is on quadratic, exponential, or power model. And so let's take a look and see what we get. So we'll go stat over, and then I'm going to do all five. So linreg, L1 and L2, cool. All right. You know what? I'm going to store the regression equation. So I'll go alpha, trace, enter. And I don't have to, but I thought it'd be cool. Okay. So linear gives us an R squared value of 0.74 81. Okay. And then we're going to do quadratic, logarithmic, and exponential, and power. And we're going to get the R squared value for each one. And that R squared value is going to tell us how good of a fit the linear function is, the quadratic function, for the data. And we just go for the biggest number. That's it. That's all we're going to do. Okay. All right. So let's run it again. So stat, right. And then this time we're going to go to quadratic model. And I'm going to store this little piggy right here. And okay, our R squared value is understandably higher. No surprise there. 0.9627. I like going 4 decimal places, just in case there's a tie, and then I don't have to calculate again. Not that it takes an awful lot of time, but whatever. I could take a look at what we got so far and say, hey, there's the linear, and yep, it sure looks like quadratic follows it better than linear, but I'll bet you one or the other is going to do better than this quadratic. I could be wrong. I don't know. I haven't done this one already. Okay, so let's go back to, okay, we need logarithmic. Okay, so ln reg, that's logarithmic regression. So I'll stick this in y3. I mean, hey, who doesn't like a good picture, right? Okay, so logarithmic regression, we get an r squared of 0.5599. Okay, no surprise that that's the worst one yet, and I fully expect it to be the worst when it's all said and done. Hey, you want to see what it looks like? Uh, okay, and oh, there it is. Yeah, it doesn't follow the points at all well, so yeah. Okay, next one, let's go stat over, and then we need exponential. I think that's 0. Yep, exponential regression. And I'm going to put this little guy in y4. Again, you don't have to do all that, all the graphing stuff, but it is, it's good to be looking at the data and, thinking about it. Okay, so, ooh, we definitely have a better one. So we've got 0.9730 is our biggest one yet. Huh, I wonder what that looks like. 1, 2, 3, and here it comes, 4. Yeah, that definitely looks the best so far. Okay, and if I go back to y equals, I can go to the equal sign and hit enter to turn off those functions, but without deleting them, and then say, all right, yeah, there's exponential right there. It looks pretty darn good. I wonder if power will do better. Okay, so I'm going to quit and go to stat over and power regression, option A. And I'll stick this little guy in Y5 because I got nothing better to do on a Thursday night. Okay. And let's see, we get 0.9905. Holy cow. Okay, looks like we got ourselves a winner. Okay, so power is the best one. Therefore, it's going to be the power model. So our equation will be y equals, and you just follow what it says. Next is A. A is, we'll just go one decimal place, 22.6. Then we're going to multiply by x, and then raise that to the b power, which is 3.2. And then that is going to be the best model out of these 5 to represent the data. Maybe there's a better one somewhere, but out of these, this is the best. There's other things we can consider, like, okay, what's going to happen to the graph of the equation as you keep going? Is it going to keep doing roughly what you're wanting, or does it, break off the beaten path? All right, let's take a look at it, the power model. There's exponential, and there goes power. So, so for the sake of a test, I would say power because it has the highest r squared value. However, there is an argument for exponential. Exponential seems to it looks like exponential, might continue to follow the data afterwards, closer than power. The gap here between the exponential model and the last point versus the gap here between the exponential model or the power model and the last point is quite a bit more. So, we would need a little more data to have an idea of how well each one performs as it keeps going. But that's how it is, and that's how it is done.